Yep, as introduced, my name is Michael Trotter. I'm going to talk to you about invisible code. You can find links to me here, as well as these actual slides. I'll have another link at the end, and I also shared them in Slack, so mainly because there are links to resources at the end. So I'm going to start with a quote. Avoid global state. Who's heard this before? 50% maybe? OK. So I don't know who said this, but I heard it a lot. I heard it in C#, I heard it in Java and JavaScript. For some reason, everyone was saying it, but I didn't really understand why. And the more I learn about it, the more I realize how much it actually affects. So the key word here is, that actually isn't in this quote, is mutable state. And it's actually any shared mutable state, but global just implies that it's shared. So we're going to talk a lot about the problems that mutable state causes and come back to that invisible code idea in a little bit. So yeah, first we'll go through individual problems caused by a shared mutable state, how you can recognize them in your code, like patterns to look for, and then how you can fix some of those things. So the first problem, mutability hides change. Say we have this code. We create an object with a sum property. We set it to 0. And then eventually, we change it to a 1. How would we figure out what the value used to be? It's pretty much gone. Like, we'd have to store the old version as a complete deep copy of the object if we knew that we needed to do this at some point. But usually, you don't do that. So we can make a slight change to this code, which is to avoid mutating that first object. We instead create a second object bound to a new variable. And now we're freely available to diff them. And you'll notice here that we're actually building off of the first object. We could copy other properties from the first object. So it's not usually a memory concern either. You get to reuse lots of stuff. But you can only make that assumption and reuse it if it's always immutable. So how do we recognize this in code? Well, this is, we're mostly just looking for like any sign of mutability. So one of the easiest ones is when you come across a function that doesn't return anything. You'll notice here that this transform function is returning undefined. That's kind of a red flag. So when you call a function, it has to do something, right? Otherwise, it's pretty pointless. And if the thing that it's doing isn't building a value and giving it back to you, then it must be mutating something behind the scenes. And we can see here that this transform function is looping through our items and setting a property on each one. So we have the same problem here that we would have in the first example. Outside this function, we can't really tell what it did, other than like stepping through it with a debugger or looking at the code itself. So the simple fix, we return the changes. Very similar function doing pretty much the same logic, but instead of actually changing the object, we're returning new ones. So we're no longer mutating these, and the new values are returned. OK, second problem. Mutability is unpredictable. So say I have this function, make cake, and I call it 3 times. And I use the same argument each time. But then I notice once I'm done that each of those returned objects is slightly different than the previous one. So obviously, this is a really simplified example, but here we've embedded this date.now call inside of our function. It's really dark. So we're reading this mutable state. Date.now is reading the current time, which is changing all the time. And reading mutable state is just about as bad as actually mutating something. Like, they both involve the same problems. And they tie different parts of your code together that you didn't necessarily intend to tie together. So how can we recognize that? Well, like we just saw, if we call the same function with multiple arguments multiple times and it gives us different results, it's probably involving some mutation. This is also called idempotence. If you read any FP stuff, you'll probably see that word floating around, but this is all it means. We see it a lot in the DOM as well, like with a query selector function. This depends on the state of the DOM itself. The result of this call could change on the millisecond. So how do we fix it? Well, we can lift the mutation up out of our function. We still have to do it somewhere, because otherwise our program wouldn't do very much. But we can try and pull it out of the business logic and up to a higher level where we can clearly see this is the point where we're choosing to read the current time. And now we get the results that we expect. So yeah, see here we're storing the date, and then we no longer have that call inside makecake. So what if I wanted to lift a write mutation? The read mutations seems a little bit easier because we get to just pass it in. But if I want to lift writing something, here we have a print receipt function. I don't know why you're printing a receipt to a console, but suppose that we are. We can see this console log call right here. I'll go back so you can actually see the code. But we're back to that same red flag as before. Console log doesn't return anything, so what's it doing? It's changing the global state outside of our program. So definitely mutating something. We can't take it back once it's done. We can't really test it unless we completely fake the whole console log object. So what we can do here is instead, we can have this function return a description of what we want to do instead. So here, instead of actually calling console.log, we return an object that says that we want to log something and the value that we want to log. And then down here, we pass that into this run commands function. And this implementation could be different for your test or your actual program. This is just kind of like taking the business logic and trying to encapsulate it without touching the outside world. We can also write it like this. All I did was take that object out into its own function. It makes the original code more similar to what it originally was. You don't have to remember what that object looks like. And there are libraries for doing this. So I've got a couple of resources here. There's more at the end, and I include these again. I just wanted to point out that this implementation is a little bit naive in these libraries. Well, the Fantasyland library has tools for doing this in a more complete way, and this FP to the max video is a really in-depth, like step-by-step guide on taking a program that's doing this like direct console writing and slowly transforming it into one that uses a pattern like this. So problem number 3, mutability adds time-dependent behavior. So I don't mean the time like we just saw, which was dealing with the date, but I mean ordering, so abstract time. So as soon as something is being mutated, reading or writing, the order that you run your lines of code in suddenly matters. So say we have these functions, red and blue. We pass the same object into both. What happens if we run them this way? We would have to read both of these functions in their entirety and understand exactly what is happening to this some data object or to the outside world. It could throw an exception. It could quietly be broken and just do something slightly different. It might just work, and we never really noticed that there was a problem or that there could be a problem. And again, we're back to kind of the same things before where these functions aren't returning anything, just the red flag is back. So to recognize this problem, this is really any shared mutable state. So we're starting to build off of our initial recognition. So how can we actually fix this? Same as before, we can use return values. So something interesting happens. As soon as we return a value from the first function, if the second function requires something of that shape, now we know what order these functions have to be run in. We can't run them in the wrong order anymore. I think that's really an interesting property. We can also write it like this. We could also write it like this. This kind of code tends to be a little bit more flexible. You can move things around more safely. Problem number 4. Mutability makes dependency trees lie. So what do I mean by that? If you remember this example, oops, I had a note at the bottom that kind of mentioned ownership. So transform, this function didn't create these objects. It doesn't know where they came from. It doesn't know all of the business logic associated with them. You could make this function dependent on all of that knowledge, but then it'd be really hard to change in the future, which is kind of the whole point. But basically, because this function didn't create them, and we don't want it to know everything about the world, it also can't really change them. It just needs to decide what the new information is based on these values and return them. So this pattern, I'm going to pick an Angular one for a little bit, because I used it a lot and I used it badly. And I don't know anything about Angular 2, so I apologize to anyone who's excited about that. But a really common pattern in Angular 1 was you get the scope object, and you get one for each instance of your controller. And the scope object, it would inherit from parent controllers, but not in a way defined by the controller. It would inherit, so this is the scope. It would inherit the scope based on your view. So this is the view. It's saying, I have this controller here and this one here. And in the middle, I can use both values. So what happens if I remove that outer controller? And if we fix that, what happens if this inner controller at the bottom, these are in completely different files, different parts of your app, but someone at some point put this line in there, which worked at the time. And then you kind of like rearrange your view a little bit, and then it doesn't work. This is that same kind of mutability issue creeping in. So here we're reading from something mutable. The scope is definitely mutable. Everything in Angular is designed around watching changes to that mutable object. So it became a really common issue. So it's basically this concept of ownership again. Are we reading from or changing something that isn't immediately relevant to the scope of the problem, or that wasn't immediately passed in as an argument? So as a similar example, here's something that's pretty common. We have this API variable. It's just a URL. We have this cache map for storing results that we get from the API. We have the simple API implementation, this get function, and it uses fetch, and it gives us back an object, well, a promise of an object. And then we have this wrapper get with cache. It's basically the same thing, but it's trying to see if it's in the cache first, and then if it's not there, it fetches it and puts it in. So does reading this API variable here involve mutability? You guess? No, because strings are immutable, and const is an immutable reference. So we can't rebind it, and we can't change it. So that's pretty safe. Okay. So how about ID? I'm going to go back to this version so you can actually read it. So the ID in the get function, this one's a little bit fuzzy. So it kind of depends on what ID is. And here we're kind of assuming it's a string, so it's probably OK. But it's interesting that we had to think about it a little bit. It could have been an object. It could have a toString method on it. Like, it's not necessarily certain. We also have this response object. Is calling .json on our response object, does that involve any mutability? Yes? No? Yes? OK. Yes, so we can only call .json one time, which means internally this response object is tracking whether you've called it that one time. You're only allowed to read it once. But something else that's interesting about this is that that response object never escapes from this callback. We kind of like, in this isolated little container, we run that mutability and then we return an object that was built off of it. And now that object is safe to pass around. We're no longer like that. The fact that it was already read, that state is not leaking out of this I'd kind of a similar question with cache. That one's, I think, pretty obvious. It's a map. It's designed to be read from and written to, and it can change over time. So if you look at this call as a whole, this is that same get function. It's interesting to think about like what pieces of this are using something mutable. And you might not necessarily want to go through the work of changing every single one of them, but it's really useful to be able to glance at it and know right away which things you're letting it do. So in this case, it really kind of depends on the API, right? If it always returns the same object and it can never change, this is like a unique ID, and we have that guarantee, then it's sort of kind of immutable. But we're still touching the outside world with fetch. If we really wanted to make this thing like testable, we'd have to also pass in the fetch function. How about this get with cache? It had a map inside. Any different? I'd kind of argue that exactly the same rules apply, because the map itself is not exposed from this context. It doesn't change the behavior of the function. We still get the same object back for the same key. So just a little exercise. So back to dependencies. Suppose that we have these three files. And B and C both depend on file A. They import file A. And you might look at that and be able to identify that just looking at your imports, or like looking at, you get a tree of dependencies from Webpack or something. But what's interesting is that as soon as A contains mutable state, the dependencies kind of go both ways. You can now write logic in file A, which specifically depends on things that are happening inside file B or file C, which means that now file B and file C also depend on each other, which is kind of unexpected. And also interesting is that files B and C can depend on each other in a way that A isn't even aware of. So you could go in and change A and not realize you're breaking both B and C. And it might be a really subtle issue. So fix for number 4, track what you are and aren't owning, make decisions about what you're allowed to touch, and be really careful about it. Generally, it's just things that you've created inside that scope. So high up in your application, you'll create like a store for your state. You'll create maybe some API config or whatever. But then you try really hard at the edges down below to pass all that stuff in and not pull it from some global place, because then it gets hard to pull things apart later. Kind of a similar example, but using a React component. This one's to illustrate that it's not necessarily different files. It could even be code within a single file that you have this kind of dependency between two things on. So here we had this file upload component. It was tracking drag state, and it was working fine as is. Okay, we've got our initial state. After a drop happens, we reset it to its initial state. But then along comes this new unrelated business logic, and someone comes in here and this file's bigger than this. This is simplified. There are other callbacks here. There's a larger render function. And the new person comes in here and they just add their logic. They just stuff it in. But they didn't know that right here, there's some logic in here that resets to the initial state. So now there's some code that's going to work on the thing that they added that they don't even know about. There's like that relationship there. So one thing we can do to fix this is using a pattern called render props in React, but there are similar things in other paradigms as well. Basically, we create this separate drag drop component that contains just this state and isolate it by itself. And then down here, you can see in this render line, we pass the state into this function. And what that looks like when we actually consume it. So here we're back in that file upload. We've taken that extra state out of this file, but now it's being passed in whenever it changes. So we've kind of disconnected that state and resetting that state and all the logic associated with it, disconnected it from our app. All we do is decide what the UI looks like every time that state changes. Okay, so problem number 5. Problem number 5 is that all of the other problems combine to increase complexity exponentially. So in real apps, like these have all been pretty condensed examples, but in real apps, your functions will be 10 to 50 lines long. Your files get to hundreds of lines long. And when everything's kind of mutating everything else unchecked, it gets really difficult to track down what depends on what and what's safe to move. And this was definitely an issue we ran into with our original naively built Angular app. It was impossible to move any forms around without completely breaking them, because they were all depending on state and validation from controllers. So I have one last example, and this one it's a summary of real-life code that existed, and the company that this code existed in no longer exists, not because of this code, but it probably could have been. So here we have the order service. We have this process order function. And again, like I just mentioned, this file is at least 1,000 lines long for some reason. This process order method is easily 20 lines long. And at some point in the middle of it, it's using these payment service calls. And what's interesting is that they're not returning anything. So it turns out that the payment service is actually storing this state in the service. So we set the current payment info. We tell it to calculate tax, and it stores the results internally. It doesn't give them back to us. We call charge later for some reason. So those are all red flags. That implementation, the way that payment service gets defined is not present anywhere in this code. It's injected by the IOC library. This is C#, by the way. So what if I told you? This is going to be like, oh, it's kind of cut off a little bit. Anyway, this is the first result for the Morpheus meme, and I thought it was funny. But basically, there's something going on here that isn't obvious in the code. And after probably like 3 days of debugging, and debugging, again, wasn't that helpful because when you're dealing with a time-dependent bug, looking at snapshots of the time at various points in time isn't always helpful. It doesn't give you like the cause and effect. So this was the source of the problem. The payment service was configured as a singleton, and someone had recently decided that the payment processor was too slow, so they told it to run on 100 threads. So you can imagine the issues involved with combining various people's orders and payment methods. And fortunately, this never went out, but if it had, it could have been really bad. So this should have been add transient, which just means it's a different instance every time something needs it. Or it could just not store that state. So this is the picture of the payment service at the time. So yeah, like I just mentioned, what's interesting about this is that if we'd used any of these techniques, like even just this seemingly simple, we don't store the state, we just return the new results. Like it doesn't really complicate the code that much. Now we can't run them in the wrong order, and we can run it on as many threads as we want without consequences. I think that's kind of cool. So to sum up, mutability hides changes, introduces unpredictability, makes code time and order dependent, and it convolutes dependencies across your apps. And all that stuff kind of grows exponentially over time as things get added without someone understanding the entire app, because that's kind of what needs to happen. I mean, it needs to happen in any case, but if you're not causing side effects, then the scope of what you need to understand is kind of contained right there in your function. So all these complexities and how they interact with each other without realizing it are what I'm referring to as invisible code. And even invisible code comes with tech debt. So I have a bunch of resources here. The video I mentioned earlier, the Mostly Adequate Guide to Functional Programming. It's very intro, it's JavaScript focused. It goes over a lot of these ideas and like the basics behind them, and then starts to build to more complicated things. Fantasyland is a library that's built on these ideas. It just gives you really, really basic building blocks that you'll kind of need some stuff from Mostly Adequate Guide to Functional Programming to understand and put together, but it's basically all of these tools in a little library. Elm is interesting. It's another language, but it makes it so that you can't accidentally mutate things you don't own. And just kind of like working with that for a little while and seeing how it can be done in that way kind of gives you a new perspective to like, oh, I could actually do this over here as well. It just makes you notice things you didn't see before. PureScript is similar, but more features. And I have to give credit to Haskell as well because it's pioneered a lot of these ideas, especially the stuff in Fantasyland. They're all kind of building on each other. And then finally, Rust has a really different, it's kind of different from everything above, and I'm sorry it's cut off, but I'll have the URL in a second. Rust takes a really interesting approach where I was talking about ownership before. And while a lot of the core FP concepts make it really hard to change things you don't own, Rust instead, in the type system, has mechanisms that track ownership. So you can either have a mutable reference, or you can share the reference with multiple things. You have to choose. It doesn't let you do both. And I think that's interesting. It kind of highlights what's going on here. But it's a very different approach. So here's the code again. Special thanks. MDX deck was really cool. It's what I used to build this. It's like Markdown and React. And then the code surfer thing you've been seeing, although I'm sorry for the highlighting. And thanks, Julia, for helping me brainstorm and review, and for all you for attending. Any questions? Okay, we got some time if there's any questions. I'm going to assume that I presented it very clearly then.
Did you come up with the term invisible code?
Yeah, I think so.
I love it.
Cool. Well, I'm going to hang out here, and if anyone wants to discuss or ask questions, feel free to come down. But yeah, thank you.